for when the eigenvalues are repeated, you have to differentiate the cofactors which you got from the first eigenvalue. It has some major drawbacks. Whereas state space analysis method gives a complete idea about the behavior of the system at any given time utilizing the history of the system. So that is a major advantage. If you see from this diagram, u of t is able to control only x1 of t. That is, if you see the output is given by the weighted sums of the x1 of t, x2 of t and x3 of t. And finding the determinant, it is found that it is 27 and it is not equal to 0. Hence, you can say that the given system is completely observable. On 0, then only you can say that the system is completely observable. It's better understood by solving the problem here. So just taking. Hello everyone and welcome back to Gyan Mastermind, an exclusive learning platform for electronics and communication engineers for GATE and ESE preparation. Before we start the session, note down the following guidelines. First guideline, use an earphone or headphone for better experience. Second guideline, take notes for better focus and understanding of concepts. Third guideline, do watch till the end of this video for immersive learning of the concepts. The last guideline, leave your questions or comments down below and I will do my best to answer them. Welcome back. Today we are going to see what is controllability and observability, an important concept in state space representation. In today's outcome, we will be acquiring the knowledge of controllability as well as we'll see Kalman's test to check the controllability and Gilbert's test to check controllability. Not only that, we are going to acquire the knowledge of observability and also use two tests to check the observability of a control system. But before we go into the actual topic of today's session, we'll see what are the two ways to analyze the control system. So the first approach is the transfer function approach and second approach is the state space analysis method. Of course, transfer function approach is a basic method. It is measured or it is specified in as the ratio of frequency domain representation of output to that of input. Though it is easy to apply, it has some major drawbacks. Whereas state space analysis method gives a complete idea about the behavior of the system at any given time utilizing the history of the system. That is a major advantage because nowadays we are going to use the state space analysis method in order to analyze a control system. So why do we need state space analysis? As I said already, the transfer function approach has major drawbacks which make it more inefficient technique that we are going to switch to state space analysis method. Coming to the first major drawback is that in transfer function approach, the initial conditions are considered to be 0, whereas in state space analysis method, all the initial conditions associated with all the elements of the control system are considered. Coming to the second major drawback, in transfer function approach, it is inconvenient for the analysis of MIMO systems, whereas in state space, it is used to analyze both SISO as well as the MIMO systems. Coming to the third major drawback is that transfer function approach is applicable only to the linear time invariant system, whereas the state space analysis, here we are going to analyze both linear, non-linear as well as time varying and time invariant systems. That is the major advantage of state space analysis method. Coming to the fourth one, it requires the transfer function approach requires frequency domain analysis. Hence, it would be difficult in finding the time domain solutions when we are dealing with the higher order systems. Whereas in state space analysis method, it is a time domain approach. Coming to the fifth drawback, transfer function approach uses some standard test input signals for the analysis of the system. Before we go into the experiment, we just test the system with a standard input signals, but it is not required in case of state space analysis method. So that is the major advantage of the state space analysis method. And coming to the last drawback, transfer function approach, it provides inaccurate response. Whereas state space analysis gives an accurate response because it involves the matrix modeling. So matrix modeling gives us an efficient computational approach and it is accurate when compared to the transfer function as well as it is applicable for the dynamic system as well. So coming to the state space model, here I have given a model for the linear time invariant system which is given by x dot equal to ax plus bu which is a state equation and y is equal to cx plus du which is output equation. So x dot is nothing but the differential state vector. This vector, that is a column vector or it may be the row vector, that vector consists of only the differential terms like dx1 by dt, dx2 by dt, dx3 by dt, etc. up to n, which is the n is the dimension of this matrix A. And coming to the x is the state vector which gives the information about the state and u is the input vector. So in this system, the output is y and input is u. And y is the output vector and A is the system matrix and B is the input matrix and C is the output matrix and D is the feed forward matrix. So D is the special matrix which you will be getting only when the transfer function, given transfer function, when the order of the numerator is greater than the order of the denominator, you will be getting the matrix D. In other cases, you will be getting 0 D matrix. You will not be getting any D matrix because this term will be 0. Du will be 0. Only y is equal to cx will be the output equation for those systems, except the system which has the numerator whose polynomial order of your numerator is greater than that of the denominator. So in those cases only you will be getting the value for this D matrix. For all other, you will be getting the output equation as y is equal to Cx. Okay. Coming to the next one, how to obtain the state space model from the given transfer function. So there are two types of transfer function based on the types of terms present in the numerator. So first case is that transfer function having constant term in the numerator. Whenever there is only a constant term, a single number in the numerator, that is considered as a case 1. And in case 2, the transfer function having polynomial function in the numerator. Whenever you come across a transfer function with a polynomial function in the numerator, that is considered as the second case. There are two cases in solving the transfer function. So here what we are going to do is that we are going to extract the state space model for the given transfer function. So when the transfer function has a constant term in the numerator, there is a method of solving that problem, and whenever you come across a polynomial function in the numerator, there is another method. Okay, so we are going to deal with these two cases. We'll solve the problem under these two cases, and then we directly jump into the controllability and observability. Transfer function having constant term in numerator. So I have given an example where g of s is equal to 1 by s square plus s plus 1. So here I am going to take this transfer function and convert into the state space model. That state space model require the extraction of state equation as well as the output equation. You have to form these two equations from the given transfer function. So the given transfer function is 1 by s square plus s plus 1, which is nothing but the ratio of output by input in frequency domain, which is given by y of s divided by u of s. And I am cross multiplying and applying the inverse Laplace transform, which would give you the d square y of t by dt square plus dy of t by dt plus y of t equal to u of t. So I am just assuming y of t to be x1. Then the differentiation of y of t is considered to be x2, and it is nothing but the differentiation of x1. That's why I have given as x1 dot. The dot represents the differentiation. And considering u of t to be a vector u. So from the first equation, you will be getting the second order differential equation is replaced by x2 dot, and the differentiation of first order differentiation is replaced by x2, and the y of t is x1 and u of t as u. So I am getting the third equation, and from the second equation, x1 dot is equal to x2. Then from third equation, I am just rewriting as in terms of x1, x2, and I am just giving it as a x2 dot. So these two are the state variables, differential state variables x1 dot and x2 dot. If you consider the given transfer function is of the order 2, because the power of s is 2. So for a given order of the system, that is 2. So we require at least the 2 state variables to analyze the systems. So this is the state equation. Capital X dot is nothing but small x1 dot x2 dot. So this is a vector. Capital X dot is a vector. And the x is given by x1 and x2. x1 and x2 are the state variables. So the state equation is given by this. See, small x1 dot is given by x2, right? So that one I have written in the matrix form. So 0 into x1 plus 1 into x2 plus 0 into u. That is given by this equation. And x2 dot is given by minus 1 into x1 plus minus 1 into x2 plus 1 into u. So that is given by this equation. Just I am representing the algebraic equation in terms of matrix format. So that gives the state equation, and from the state equation we know that the standard format is ax plus bu, right? So from this, the A matrix is nothing but 0, 1, minus 1, minus 1, and the matrix B is given by 0, 1. Then comes the output equation. So the standard format is y is equal to cx plus du. I have to bring the equation in this format. Okay, so for this, so as of now, we have solved the matrix A and B. We have got the matrix A and B. Now we are going to determine the matrix C and D. So how to determine the C and D is, as I already said, D will not be, you will not be getting the D matrix here, because the order of the polynomial in the numerator should be greater than the order of the polynomial of the denominator. Okay, so only in those cases you will be getting the matrix D. Here there is no chance of getting D. So D will be 0 here. And I am just as already assumed y of t to be a vector y, and it is given by x1, and x is nothing but the two variables x1 and x2 state variables. Then from the output equation, standard format output equation, I will be getting y is equal to 1, 0, x1, x2, which is the output equation, and from this I will be getting the matrix C. So this is the transfer function block diagram. The equivalent block diagram is given by this. See, I have assumed y of t to be x1 of t. So I am just writing this one, and the differentiation of x1 of t is given by x2 of t. That's why I have introduced the integral block diagram. because x2 of t when integrated will get the x1 of t. By differentiating x1 of t in the reverse order, you will be getting the x2 of t, and by differentiating x2 of t, you will be getting x2 dot of t. And then these x2 of t and x1 of t are sent back to through negative feedback and added with the input, which will yield the x2 dot of t, which is the same equation I have given here. If you see, x2 dot t, x2 dot equal to minus x2 minus x1 plus u. That's what I have given here. See, it is a negative unity feedback is sent and then added with the input u, and that gives the x2 dot of t, and y of t is nothing but x1 of t. Transfer function having polynomial function of s in numerator. So consider this problem with g of s equal to s square plus 3s plus 5 divided by s cube plus 4s square plus 5s plus 2. So I'm just going to bring this one in this format. That is, I'm just going to transform the transfer function approach to the state space model. Here I'm going to represent in state equation and output equation, simply such that I'm going to form this one into this equation and get extracted this A matrix, B matrix, C matrix and D matrix. As of now, you will not be getting the D matrix, because as I already told you that whenever the numerator, the polynomial order of the numerator is greater than that of the denominator, you will be getting the D matrix. But as of now, you will not be getting the D matrix. The output equation is simply y is equal to Cx. So I'm just rewriting this y of s by u of s as b of s by u of s into y of s by b of s, just introducing an intermediate output b of s, and just separating the denominator term and numerator term separately, because the denominator term contains the most of the information of the control system, and thus I'm just going to get the state equation from this denominator term and output equation from the numerator term, considering the intermediate output b of s. You will better understand when we proceed. So coming to the block diagram, this is the simple block diagram of the given transfer function of the given system, and then I'm just separating into two blocks, first involving the denominator term and second involving the numerator term, and the intermediate output function is b of s. As of now, just consider the first block diagram. Here the input is u of s, output is b of s. So b of s by u of s is equal to 1 by s cube plus 4s square plus 5s plus 2. On cross multiplying and taking Laplace transform, you will be getting this differential equation. And from this I am making assumption that v of t is equal to x1, and the first order is given by x2, which is nothing but x1 dot. The dot represents the differentiation term. And the second order as x3 and which is nothing but x2 dot, and the third order is given by x4, which is nothing but x3 dot. And considering u of t to be u vector, so from these I'll be getting the differential vector as x1 dot, x2 dot, x3 dot, whose equation is x1 dot equal to x2. See, x1 dot is equal to x2. x2 dot, what is x2 dot? x3. x3 dot, what is x3 dot? x3 dot you will be getting by rewriting this actual inverse Laplace transform equation. So just making this one in the left side and bringing all other things to the right side, you will be getting this equation: minus 2x1 minus 5x2 and minus 4x3 plus u, and v is nothing but the x1. See, here I have made assumption that v of t is equal to x1, right? So v is equal to x1. So from this, I'll be getting the state equation like this. See, x1 dot is equal to x2, right? So x1 dot equal to 0 into x1, 1 into x2, 0 into x3 plus 0 into u. So that will be giving your first equation. So what is x2 dot? x2 dot equal to 0 into x1, 0 into x2, 1 into x3 plus 0 into u. That is the second equation. And coming to the third equation, x3 dot. x3 dot equal to minus 2 into x1, minus 5 into x2, minus 4 into x3 plus 1 into u. So you will be getting this third equation. Just I am going to represent this equation in terms of matrix, that is in form of state space model. Coming to the output equation. Output is nothing but b is equal to x1, right? So this is not an actual output equation. This is an intermediate output equation, which I am assumed v of s to be the intermediate output, right? So v is nothing but x1. So 1 into x1, 0 into x2, 0 into x3. Other terms will be cancelled out, which will yield you v is equal to x1. Just I am representing this in terms of matrix. Coming to the second block diagram. Here the intermediate output is given as input to this block diagram, and the actual output is y of s. So the ratio is given by s square plus 3s plus 5. Sorry, here the 4 is not there. This is nothing but s square plus 3s plus 5. Just ignore this 4. It is a printing mistake. Then y of s is given by this one, and taking Laplace transform, inverse Laplace transform, you will be getting this one. Y of t is equal to d square v of t by dt square plus 3 into dv of t by dt plus 5 into v of t. So just making assumption y of t to be y and the first order to be x2, which is nothing but x1 dot. These assumptions I have made already. just rewriting this, and p is nothing but x1 as we have seen in the previous slide, which will yield you the output equation as y is equal to x3 plus 3x2 plus 5x1. So from this output equation, we'll be getting y is equal to 5 into x1 plus 3 into x2 plus 1 into x3. So drawing an equivalent block diagram for the given transfer function. So here I'll be considering the intermediate output v of s to be x1, right? So x1 of t is nothing but v of t, and the differentiation of x1 of t is given by x2 of t, and its differentiation is given by x3 of t, and the x3 of t differentiation is given by x3 dot of t. So the negative feedback and a weight of the coefficients. See, the coefficients of this is, see, the coefficients are 4, 5, 2, right? So those coefficients are written in this feedback, 4, 5, 2, and those are added with the input to get the x3 dot of t. And if you see the output is given by the weighted sums of the x1 of t, x2 of t and x3 of t. See, this is what I have given here, 5, 3, 1. These are the weights of the x1 of t, x2 and x3. Coming to the actual topic of the today's session, which is controllability. So what is controllability? Any system which is controllable is called the controllability. So if a state of the system can be changed to another desired state in the presence of reference input in the finite time duration, then such a system is known as completely controllable system. So the controllability of a system can be checked by the two types of tests. One is given by the Kalman's and another one is given by Gilbert's. So we'll be seeing more detail about these two tests. So before that, we'll see what is the controllability in deep. See, if you see in this SFG, this is the input u of t and y of t is the output. So u of t is going to control the system. So if you see from this diagram, u of t is able to control only x1 of t. That is, it is able to control only the affects only the state x1 of t. The state x2 of t is uncontrollable. You cannot control the state of x2 with u of t. It would be impossible to drive x2 of t from initial state x2 of t naught to the desired value x2 of td in a finite time interval. So in a finite time interval, you cannot change the states of the x2. So the whole system is uncontrollable. Coming to the Kalman's test to check controllability. So the procedure involving in Kalman's test is given by, first step is that you have to find the system matrix A and input matrix B from the state equation. So this is the state equation. You know that the matrix A is n into n. It is of order n, and B is n into 1 in our case, and this is a vector which is given by n into 1. So first you have to get the matrix A and matrix B. Then you have to form a controllability matrix QC, which is given by B, AB, A square B, etc. up to A n minus 1 into B. So the order of QC will be the same as that of the order of the matrix A. And then you have to find the determinant of QC. Okay? So when the determinant of QC is not equal to 0, then you can say the rank of QC is n, and also all the n number of states are controllable. That is, the whole system is controllable when the determinant of given QC is not equal to 0. Suppose if the determinant of QC is equal to 0, then you can say that the rank of QC is not equal to n, and you can say the system is uncontrollable. Even if the system is uncontrollable, if you want to find how many states are controllable in that system, it is given by P. For that, what you have to do is that you have to form a submatrices of QC of order n minus 1. Suppose the order of QC is given, QC is 3, you have to form a submatrix of order 2 cross 2. You have to form submatrices n number of submatrices such that you have to find determinant for each submatrices. If any of the submatrices is not equal to 0, then you can say that the number of states is given by P, which is nothing but n minus 1. And if the determinant of that submatrix is equal to 0, then again you have to form the submatrices, so which is of the order n minus 2. So you have to find the determinant for those submatrices, and if those submatrices is not equal to 0, you can say that the number of states controllable is given by n minus 2. Otherwise, you have to continue this procedure until you get the non-zero determinant. So this is the actual procedure. Just have a look and read it. You can have a better idea. A problem to check controllability by using Kalman's test. This is a state equation which I have taken from the previous problem, from which I'll be getting the A matrix and B matrix as like this. and then I will be forming the controllability matrix just to test whether this system is controllable or not using Kalman's test. So for this I will be going to form a controllability matrix which is given by QC, and the order is n is equal to 3 here. We have to check whether the determinant is not equal to 0. Here the matrix B is directly given, and AB is nothing but 0, 1, minus 4, and A square B is nothing but 1, minus 4, 11. So QC is given by B. What is B? 0, 0, 1. And what is AB? AB is 0, 1, minus 4, 0, 1, minus 4. And what is A square B? See, the term stops at this stage because n is equal to 3. So A square B is 1, minus 4, 11. That's what here, 1, minus 4, 11. On finding the determinant, it is found that 1, which is not equal to 0. Hence, we can say that the given system is completely controllable. Coming to Gilbert's test to check controllability. So, whenever you are going to check for controllability, you are going to take the state equation alone because we need the matrices A and B alone. Only for checking the observability, which we will be going to see in the next session, there only we need both the state equation as well as the output equation. So as of now, to check the controllability, it is enough to analyze the state equation alone, because we need only the A matrix and B matrix to check the controllability. To check the observability, we need both state equation as well as the output equation, because we need the C matrix also. Coming to the Gilbert's test to check controllability, first you have to find the eigenvalues of the system matrix A using this formula. That is lambda I minus A equal to 0. I is nothing but the identity matrix, lambda is the eigenvalues, lambda I minus A, that is modulus. You can also write it as A minus lambda I, whatever it is. By equating to 0, you will get a equation, algebraic equation, from which if you solve that, you will be getting the roots of that equation. And second one is that form the model matrix or diagonalization matrix which is given by. So model matrix is used to diagonalize a given matrix. So which is nothing but M is given by M1, M2, Mn for n, where M1 is the vector which is nothing but the cofactors of the first row of the lambda 1 I minus A matrix. It would be somewhat confusing for you, but actually when you solve the example problems, you will be very clear about this. See, first taking the eigenvalue lambda 1, you will be getting n number of eigenvalues, right? An equation might have n number of eigenvalues. So depending on that, first take the first eigenvalue and then form this matrix, and from this matrix you have to find the cofactors of the first row of that matrix, which will give you the M1 vector. And the same thing, M2 is nothing but the cofactors of the first row of the lambda 2 I minus A matrix. So taking the second eigenvalue and substituting in this formula, you will be getting a matrix, right? So from that matrix, considering the first row, taking cofactors of the first row of that matrix will give you C11, C12, C1n, etc. So that will give you the M2 vector. So the combined vectors of these will give you the model matrix. You'll be clear when you solve the example problems. And the third step is that. So as of now, you have formed the model matrix. So model matrix is nothing but it is used to transform a matrix or it is used to diagonalize a matrix. So for that, we are going to first construct this M matrix and then take the B matrix multiplied by with it. See, compute B, which is given by B is equal to M inverse into B. So B vector is given by, you have to take inverse of that model matrix and multiply with the B matrix. The necessary condition of complete controllability is simply that the vector B should not have any zero elements. If this vector, that is B vector, doesn't contain any zero elements, then you can say that the system is completely controllable. So we'll solve one example so that you can have a better idea. Before that, you have two cases. When the system has distinct eigenvalues, when the system has repeated eigenvalues. You will get two cases. Just listen here. When the system has distinct eigenvalues and when it has repeated eigenvalues. So, see, I have told you for extracting the eigenvalues, you need this equation, right? So, by solving this equation, you will be getting the n number of eigenvalues. If those n number of eigenvalues are distinct, you will have a method to solve it. And if it is repeated, if the eigenvalues are repeated, you will have a different method to solve it. You will get a clear example of this by solving the problem. So a problem to check controllability by using Gilbert's test. I'm just taking the same problem. From this I'll be extracting the A matrix and B matrix. For checking the controllability, I already said that we just needed only the state equation. So this is the formula for getting the eigenvalues, which is given by lambda I minus A equal to 0. Now substitute for identity matrix and solve it, get the determinant, you will get the equation like this in lambda. When you solve this equation and just solve using a shortcut method, see I have this is a cubic equation, right? So writing the coefficient of this one 1, 4, 5, 2 here, and then assuming some values for lambda such that it becomes 0. So here I will be getting the lambda is equal to minus 1. I just got the 1 root by assumption and then substituted here I will be getting the 0. So lambda is equal to minus 1. Here we have to choose a number such that the last term will become 0. So for 2 to become 0, I have to write minus 2. Then add it with the second term 5. 5 minus 2 will give you 3 and write it as minus 3. And add with this 4 minus 3 will give you the 1 and write it as minus 1. And minus 1 add it with this one will give you 0, write it here. Then add these terms. Ignore the 0. 5 minus 3 will give you 2. 4 minus 1 will give you 3. And 1 minus 0 will give you 1. So from this you will be getting the quadratic equation x square plus 3x plus 2. Or here lambda square, right? So lambda square plus 3 lambda plus 2 equal to 0. You will be getting a quadratic equation as well as multiplied by lambda plus 1. So this is the equation, actual equation, cubic equation. From this I have solved for the eigenvalues. So which is given by lambda plus 1 into lambda square plus 3 lambda plus 2 equal to 0. So this is quadratic equation. You can solve it easily. So just follow the steps. You will be getting lambda 1 as minus 1, minus 1, minus 2. So lambda 1 and lambda 2 are same. Minus 1 is repeated and lambda 3 is minus 2. Now we have to compute the B matrix, which is given by the M inverse B. So before we compute B, we need the M matrix, right? So for constructing the model matrix, which is M, you have to follow these steps. So M is given by the M1, M2, M3. So where M1 is a vector and M2 is another vector and M3 is another vector. Since here N is 3, if you see the dimension of A matrix, it is 3, right? So M1, M2, M3. Lambda I minus 1. Just consider the lambda I minus 1 as this one. Just substitute this one. You will be getting the model matrix model vector. M1 is given by the vector C11, C12, C13, where these are the cofactors of the first row of this matrix. Cofactors of this matrix, that too for the first row. By solving this, you will be getting C11 equal to, this first element is C11 is given by plus 1 into lambda minus 1, 5 lambda plus 4. On solving this, you will be getting an equation here. And the next cofactor C12 is given by minus 1 into, because it is in the second place, right? So minus 1 into 0 into lambda plus 4, 2 into minus 1. So on solving this, you will be getting the minus 2. C13. So cofactor of this one is nothing but 5 into 0 minus lambda into 2. So which you will be getting minus 2 lambda. So I got the elements of M1 vector. So which is nothing but lambda square plus 4 lambda plus 5 minus 2 lambda. Substituting lambda 1 equal to minus 1, you will be getting the M1 as 2 minus 2, 2. So what is the vector M2? So vector M2 is repeated, right? The second eigenvalue is repeated, that is minus 1. Minus 1 is repeated 2 times. So M2 is got by differentiating this cofactor d by d lambda 1 C11, d by d lambda 1 C12, d by d lambda 1 C13. So on differentiating these cofactors, you will be getting this. See, this is the equation you got for M1. By differentiating these things, you will be getting the M2 vector, which is given by 2 lambda 1 plus 4, 0 minus 2. And substitute for lambda 1 equal to minus 1 here, you will be getting the M2 as 2, 0 minus 2. So this is the method. This is the difference when you encounter the repeated eigenvalues. When the eigenvalues are distinct, you proceed as it is. But for when the eigenvalues are repeated, you have to differentiate the cofactors which you got from the first eigenvalue. Coming to the third eigenvalue. Third eigenvalue is distinct, right? So it is different. So the substitute directly in this formula, you will be getting the matrix, and from this matrix you find the cofactors of the first row. So C11 is given by -2, -1, 5, 2, and C12 is given by 0, -1, 2, 2, and C13 is given by 0, -2, 2, 5. Okay, just find the cofactors of the first row. You will be getting the M3 vector. So now you have found out all the vectors, M1 vector, M2 vector, M3 vector. Since the eigenvalue 1 and 2 are repeated, we are going to introduce the differential term here. Just form the equation. Don't substitute directly lambda 1 in the first itself. Just form the equation and then last substitute the lambda 1 value. For the second vector which is repeated, for this find the differentiation of these equations and then substitute the value of lambda 1, which will give you the M2 vector. Now you have found out M1 vector, M2 vector and M3 vector. Now form the model matrix. M is given by M1, M2, M3. So this is the matrix you got for the M. Now our actual process is what? We have to compute B, right? Which is given by B vector is given by M inverse into B. So we have to find the inverse matrix of the M matrix and then multiply with B matrix. So for finding M inverse, the formula is 1 by determinant of M into edge of M, and determinant of M is 4, cofactor of M, you will be getting this one, and taking transpose you will be getting this one. So this is the edge of M. So the M inverse is given by 1 by 4, minus 4, minus 10, minus 4, 4, 6, 2, 4, 8, 4. By taking 4 inside, 1 by 4 inside, you will be getting this matrix. And now we are going to compute B vector, which is given by M inverse into B. And if you find this one, multiply the M inverse with B, you will be getting the answer -1, 0.5, 1. So which are not equal to 0. If you see, all the rows are not equal to 0. Hence, the given system is completely controllable. Yes? So, first you have to find the eigenvalues, then check whether the eigenvalues are repeated or distinct, and then form the model matrix accordingly. That if the eigenvalues are repeated, you have to form the model matrix such that you have to consider the solving the differentiation of the cofactors. You have to form an equation for the cofactor and differentiate it for the repeated eigenvalues. When the eigenvalues are distinct, directly substitute in the lambda I minus A equation and then form the matrix, then find the cofactors to form the model matrix. And from the model matrix, just multiply with the B, which would give you the B vector. Check whether the B is not equal to 0. B vector is not equal to 0. You have to check for all the rows. Only if all the rows of the B vector is not equal to 0, you can say that the given system is completely controllable. Yes? Coming to the observability. So what is observability? A control system is said to be observable if all the states of the system can be determined from the knowledge of the output of the system at a given time. If you know the output, you will be able to determine all the states of the system. The concept of observability says that a system is completely observable if every state variable of the system affects some of the outputs. So the output is directly related to all the state variables. To consider this SFG, here the input is U of t and output is Y of t. If you consider the system, by knowing the output, you can estimate the state of the system, which is x1, not the x2. You cannot directly estimate the state of the system x2, hence you can say this system is unobservable. It will be clear when you solve the exam problem. Kalman's test to check observability. You have to take both state equation and output equation when you check for observability, as I already told you. The first step is to find the system matrix A from the state equation and output matrix C from the output equation. So you need this A matrix and C matrix. A matrix is of order n and C is 1 by n. And from the matrices, you have to form a observability matrix, which is given by Q0 equal to C transpose, A transpose, C transpose, A transpose whole square into C transpose. That matrix goes on till n minus 1. So now you have to find the determinant of Q0, and if Q0 is not equal to 0, then rank of Q0 is n and all the states are observable. So this is the same procedure what we have seen in controllability. And if the determinant is equal to 0, what shall we do? We have to form the submatrices to find the remaining number of states which is observable. Okay, yeah, we have proved if the determinant is equal to 0, we can say that one of the states is unobservable and remaining for checking remaining states is observable or not, we have to form the submatrix and find the determinant for each submatrix. And if it is not equal to 0, you can see that the remaining number of states are observable. If the submatrix determinant is equal to 0, then you have to form sub-matrices and then follow the same procedures till you get the non-zero determinant. So these are the procedures are the same because it is a Kalman's test, right? It is a Kalman's test. Just the difference between the checking of controllability and observability is that there you are forming a QC matrix, here Q0 matrix. Just form the matrix and find the determinant whether it is equal to 0 or not equal to 0. So coming to the problem. So here this is the state equation I have taken and the output equation. So from the state equation I will be getting the A matrix, and from the output matrix I will be getting the C matrix. So C is 5, 3, 1 and A is 0, 1, 0, 0, 0, 1, minus 2, minus 5, minus 4. So this Q0 is the observability matrix which is given by this one. So from this I will be just forming the C transpose and A transpose into C transpose, which is given by this one, and A transpose whole square, because Q0 stops by this, right? Because n is equal to 3. So C transpose, A transpose, C transpose, A transpose whole square, C transpose, because n is equal to 3. And the order of the matrix is given by 3, which is same as the system matrix A. Q0 is nothing but 5 minus 2, 2, 3, 0, 3, 1 minus 1, 4. And finding the determinant, it is found that it is 27 and it is not equal to 0. Hence, you can say that the given system is completely observable. Coming to the Gilbert's test to check observability, as I already told that for checking the observability, you have to consider both state equation as well as the output equation, because you need the A matrix as well as the C matrix. So for this, the same steps as that of the controllability, the Gilbert's test, you have to find the eigenvalues using this formula lambda I minus A equal to 0. You will be getting the n number of eigenvalues, and you have to form the model matrix or diagonalization matrix, which is same. You have to find the cofactors of the first row of the eigenvalue substituted in that matrix, and the second eigenvalue substituted in that matrix. Find the cofactors of the first row, that will give you the second M2 vector. So you have to find all the vectors and form the model matrix. And from the model matrix, what you have to do is that you have to take the C matrix. Okay, you have to take the C matrix and multiply it directly with the model matrix. In the controllability session, there we are going to multiply M inverse into B, but here we are going to multiply directly with the model matrix. We have no need of finding the inverse of model matrix. Just multiply the model matrix with this C matrix. The necessary condition for complete observability is that none of the columns of the matrix C is 0. If none of the columns, okay, all the columns should be non-zero, then only you can say that the system is completely observability. It is better understood by solving the problem here. So just taking the same state equation and output equation A, B, C, D is 0, and forming the model matrix which is given by this one. That is this one I found out in the previous problem, right, in controllability session. So we have to compute C is equal to Cm. So the C vector is equal to Cm. Here just substituting directly the C and M model matrix, will be getting the answer is 683, which is not equal to 0. So none of the columns of the matrix C is 0. Hence you can say that the given system is completely observable. Hence in this session we have found out what is controllability and the Kalman's test and Gilbert's test, as well as we have acquired knowledge about the observability also, and the Kalman's test to solve to check the observability of a control system, as well as the Gilbert's test.
Alright, that's all for the session. So I hope to see you in the next session soon. Thank you all for watching. To stay up to date with the latest videos, make sure to subscribe to the channel by clicking the red button below this video and hit the bell icon. Thank you.